This week we're going to talk about magnetic declination, how to find out what it is at some point on the Earth, and how that might change the wind observations that you're using. Welcome to another MetPy Monday. Hello, I'm John Lehman, a software engineer for Unidata. This week I want to show you a way to find the magnetic declination wherever you are on Earth, because that could modify how you're using wind observations. And we'll talk about that a little bit more at the end of this notebook, exactly what situations you do and don't need to worry about this. But it's also just a handy thing to know. I've got a map here from the USGS that shows very coarse contours of magnetic declination over the US. So we've got the 0-degree declination line, which is called the agonic line, or no declination. And then we've got all of these isogons, or isogonic lines, that show how much the magnetic declination varies between true north and magnetic north. I actually had some data I needed to process, and I knew that it was aligned with magnetic north. I wanted to correct it to true north. So I needed a way to programmatically get the declination, and I thought about writing my own interface to some of these magnetic models that are out there. But of course, one of the great things about open source is somebody already has done it. In fact, there are a few different packages out there. The one that I ended up using is called Magnetic Field Calculator. And there's some great little examples in the docs, and it's very easy to install. To install, we just type pip install magnetic-field-calculator. So it's a little bit of a mouthful there, but it's still pretty easy and installs with no issues, and has been updated more recently than many of the other packages that are out there. It can also use different models. By default, we're going to use the World Magnetic Model in the most recent version, but there are examples in the docs how if you're going back in time and you want to maybe see what a model from 10 years ago said, there are ways to do that. But we're going to focus on correcting observations now, or very close to now. So to use this, the first thing we need to do is import the magnetic field calculator object from the magnetic field calculator library. So from magnetic field calculator, we're going to import the magnetic field calculator object. And then we're going to create an instance of that object and just call it calculator. All right, so to start off, we're going to do a very simple calculation. We're going to try to determine what is the magnetic declination in Boulder, where Unidata is located. So we're going to call our calculator the calculate method. Latitude is equal to 40.015. Longitude is equal to 254.73. And what we get back is a dictionary of dictionaries. If we look inside it, we see that we're using the World Magnetic Model, the 2020 revision. It's always going to default to the most recent revision, unless you specify an older version. It'll ask you for a date. It's going to assume today. As you can see, we're very near the end of 2022. The coordinates, we didn't give it an altitude. We can. And then it breaks down a lot of things like what is the field value to total intensity, the declination, the inclination, north intensity, east intensity, vertical, horizontal. So it does all of that trig for you. And that's really actually very interesting to look into, but all we're interested in here is what's the declination. And we're not interested in even what's the change of the declination, which it gives us here, and how many arc minutes per year the declination is changing. So we can get the declination by looking at the field value dictionary, and inside the field value dictionary, getting declination. And there we see that we get 7.398 degrees east. We can add some more details if we'd like. And actually, altitude is one of the interesting ones because I couldn't find any documentation. If we look at the function signature of what it says, height above mean sea level where magnetic values are requested. In what units? This is not a unit-aware library as far as I'm aware. So how can we tell? Well, we can experiment, which I did some of, but also look at the results, because generally you get what the library wants to be given back. And here we can tell that we're getting 0 kilometers is the default altitude. So we need to specify altitude in kilometers. I'm going to save myself a little bit of typing here. And for Boulder, we're looking at about 1.62 kilometers. And if we look at our result, 7.934 versus 7.938. So it's a very small change based on the altitude, and that's a pretty significant altitude. Now, I had originally assumed, before I did a more detailed examination, that this was in meters. If we put 1,620 in, thinking that this is in meters, not kilometers, you can tell we get a very wrong answer, over 2 degrees incorrect, because we're way high. So it's always important when you're using a new library like this to verify it against something that you know. And one of the things that I knew was looking at this map that Boulder should be closer to 10 than 5. So I thought something might be suspicious. I actually pulled up a map from the FAA, which has the isogonic lines drawn and updated very frequently, and confirmed that and said, something must be wrong. Started looking in here and getting what was going on. Also, notice that it's in degrees east for longitude. And from my experimenting, if we enter a negative longitude, it does not convert that to west for you. So a few limitations to the library, but it's very simple to use and it seems to work quite well. So why do you care about what the magnetic declination is at your location? Well, things like ATIS, AWOS, ASOS, and pilot reports, which we sometimes use, are all referenced to magnetic north. Those AWOS and ASOS stations are just aligned with a compass to north. Now, if you're getting your data from a METAR, that has been corrected to true north. A terminal area forecast, forecasts in general, models commonly, like the GFS, or winds aloft forecasts are referenced to true north. So if you're wanting to compare, say, a METAR to something that or maybe a TAF would be a more common example. I want to do some forecast verification. How do my TAF compare to current data I'm getting directly from an ASOS station, not via a METAR? You're going to get a significant wind variation unless you correct that. Now, I don't know a lot of people that are getting AWOS ASOS data directly, not just via a METAR. But what I do know is a lot of you watching go and do field projects. And a lot of field projects align the instruments to magnetic north. That's easy to do in the field. Or they even have a magnetometer on the station that measures the orientation of the station, temporary station, when it's deployed with respect to magnetic north. So this is a very easy way to do that correction. And how to apply the correction? The saying has always gone, east is least, but west is best. And that's going from true to magnetic, because generally we're measuring something on a map, and we want to get from A to B, and now we need to know what magnetic heading to sail. So east is least, but west is best means we subtract east variations, add west variations to go from true to magnetic. And to go from magnetic to true, it's the opposite of that. You add the east variations and subtract the west variations. So I hope that you found this useful. This is a really handy little library that is a good thing to keep in your back pocket when you need to correct some data that you're getting from a source that specifies wind direction in magnetic north. I hope that you found this useful. I'll see you on next week's MetPy Monday.